Hello, this video is meant to review some concepts from the energy model. Specifically, we didn't talk too much about the equation where we say that work equals force times distance. So this problem set is meant to practice using that particular portion of the equation, although there are one or two of these that don't involve work at all. So this first one here, we have a 1,000 kilogram car. It says it's traveling 75 miles per hour at 33.5 meters per second. When it crashes into a group of water barrels on the median of a highway, and it comes to rest over a distance of 20 meters, and I'm assuming the barrels are outside of the system. And so basically what's inside the system is the car. And you have to think here, what sort of energy would it have originally? Well, originally the car is moving. We're not going to say it's at any sort of special height or anything like that, so originally it should just have E-trans. All right, translational kinetic energy. In the end, if you think about the car and what sort of energy it would have, you might think thermal, and you're probably right, it would have a little bit of thermal there, but mostly it's lost the energy that it had when it was moving, and where that energy has gone is to the barrels. All right, so there are these barrels outside of the system, and the barrels received energy from the car. And so what we'll do is we'll say, all right, that 4 units of energy that we had here, that's going to go out of the system to these water barrels that are sitting at the car, and then there's nothing there in the end. And so the way that we write out this equation then is that the initial translational energy, E trans I, equals the work that the car did on the barrels. All right, so that's what we end up with. To calculate the original translational energy, we have to use the translational energy equation, which is 1/2 mv squared. So we know 1/2 times the mass of the car, which was 1,000, times its velocity in meters per second squared, which is 33.5 squared. All right, we know that equals the work, which is force times distance. So in this case, force times 20. I'll just point out here that we've got FD. So the only unknown here is the force. So you just multiply there on the right and get 1/2 times 1,000 times 33.5 squared and divide it by 20. And you should solve this and find that F equals 28,056 joules. I'm sorry, that would be newtons if it is a force. All right, for problem number 2, it says a 60 kilogram student jumps from a 10-meter platform into the pool below. It says how much EK, and EK here means E-trans, does she possess at impact? Well, there's no LOL chart for this one, but something that you need to keep in mind is that whatever gravitational energy that she had originally, all of that is going to become translational energy. So whatever EGI, initial gravitational energy she had, that's going to become her final translational energy. So the first thing that I'll do then is I'll say, all right, well, EGI equals her mass times her gravity times the height that she was at, which is 60 kilograms times 10. All right, and the height was 10 meters. All right, so what we end up with here is 6,000 joules. And that also equals her translational energy. All right, so that's how much EK she ends with at the end, how much E-trans she ends up with at the end. For part B here, it asks what was her final velocity. Well, this question here then is having us break down that E-trans a little bit more, right? So we know E-trans equals 1/2 times mv squared. So we know that 6,000 equals 1/2, and then again her mass is 60. Times velocity squared. And if you go through that, you should find that her final velocity equals 14.1 meters per second. See here, it's squeezed in right at the bottom. It says, how much force does the water exert when she comes to a stop in the bottom? And so this was another one that we could have done an LOL chart for. But what's happening is she had 6,000 joules of translational energy just before she hit the water. After she hit the water, that translational energy was transferred to the water. She would be like swirling around, the water would be moving, but she ends up stopped in the end. So in the end, she doesn't have any translational energy. If she comes to a stop in 2 meters and it's taken her translational energy away, then we're going to say, all right, then that work here, in this case, must equal the 6,000 joules that she had. Also, we know that work equals force times distance. All right, so you can use those two things together to solve for force, and you get that force equals 3,000 newtons. Now, if you wanted to do a more complicated version of this problem, you would take into account the fact that she had gone down 2 meters, which means that there was actually a bit of a change in gravitational potential energy here as well. I decided to go with the simpler version where we ignore that change in gravitational potential energy because it'd be pretty small. But technically speaking, if she's going down in the water and she comes to a stop in 2 meters, you might have included the gravitational potential energy there. For problem number 3, we've got a spring here whose spring constant is 850 newtons per meter and is compressed to 0.4 meters. And I'm asking what maximum speed can it give to a 500 gram ball. So in this case, what we're dealing with here is we say the initial spring energy, the initial elastic energy, equals the final translational energy. So this one doesn't have anything to do with the work equation. So we have 1/2 kx squared then equals 1/2 mv squared. You can drop the 1/2s. I'll actually probably just leave it just for continuity, but you can get rid of the 1/2s because they're on both sides. But we'll say 1/2 times the k, which is 850, that's the spring constant, times the distance that it was stretched or compressed, which is 0.40, squared equals 1/2 times its mass. It's 500 grams. You got to convert that to kilograms, so it's 0.5 kilograms times the velocity squared. Right, so you go through and you should solve this for v, and when you do that, you should get that the velocity equals 16.5 meters per second. Sometimes people make an algebraic error in calculating this, and a lot of times it has to do with squaring it or taking the square root, and just make sure that you've done that if you're not getting that correct answer. And if you struggle to get any of these, you can always come in and ask. So on to the back here, problem number 4. This one is probably the most ambiguous problem on the sheet because it involves a gun, and there are different kinds of guns and they work differently. What I would say is we're going to interpret this as there's an old-fashioned gun where you would like load the gunpowder first and then put the bullet in and then shoot it. And it says, in this case, you're including the bullet in the system, all right, but the gun exists outside the system. And I'm going to say the gunpowder also exists outside of the system. And so if you think about this bullet that's just sitting there before being fired and what type of energy it would have, it actually doesn't have any type of energy. Some people might think gravitational potential energy because normally you would hold a gun up off the ground. But as you're firing a gun, when that energy is being transmitted from the chemical gunpowder to the translational energy trying to make the bullet move, there's not really a change in height that the bullet experiences, right? When the bullet is in the barrel of the gun, its height is staying relatively constant. So we're going to say that zero reference line is right where the bullet starts, which is even with the height of the gun. And therefore, I would not say actually that it has gravitational potential energy because it's not really moving up or down as it goes through the barrel of the gun. So there's not really actually anything here in terms of its original energy. What happens then is that the gun goes off and it gives the bullet energy. I'm going to say 4 units of energy, all right, from the gunpowder going off. Then in the end, what we've got here is we've got a bullet that is moving. So I'm going to call that E trans because when an object is moving through space, we call it translational energy. This problem asks what speed will the bullet reach when it's leaving. So first we need to make an equation from this. We know the work done by the gun on the bullet is equal to its final translational energy, E trans F. All right, and if we calculate that then, we can do force times distance. Work equals force times distance. So I'll just write it out. F times D equals 1/2 mv squared. The force is 5,500 newtons. Times the distance. We look there at the barrel length of the gun. If you look up above, it says that it is 85 centimeters long. So 85 centimeters is 0.85 meters. All right, so that's our force times our distance. That equals 1/2 times the mass of the bullet. It says it's, again above, it says it's a 10-gram bullet. All right, so 10 grams is 0.01 kilograms times its velocity squared. Go through the algebra of that and solve for the velocity, and you should get a velocity of 967 meters per second. Number 5 here, we've got a ball that's dropped from a height of 1.5 meters, and this is similar to a problem that we saw earlier in one of the energy packets. It bounces back up, but it only reaches a height of 1 meter. You have to think, what's happening here with the ball? If it started at 1.5 meters and then it bounces back up to 1 meter, what's happening is that it's losing some energy to friction because of the distortion of the ball when it bounces on the bottom of its bounce. The ball gets sort of crunched up at the bottom and then it springs back out, and there's some distortion in the shape of the ball as that happens, and it creates friction, which is a thermal sort of interaction, and so we end up with some energy that's lost as that ball bounces. And you should be familiar with this in your everyday lives. When you drop a ball from a certain height, it doesn't bounce back up to the original height that it was at. So what we have then, originally, it's got gravitational energy because it's held at 1.5 meters, so we've got Eg on this side. In the end, it's got Eg as well. All right, but that Eg is not as high. All right, because it does not bounce as high, so we've got Eg here, and then there's going to be a little bit of thermal as well, because that energy is lost to some thermal energy. And so then we know Egi equals Egf, the final gravitational energy, plus E therm F. We can figure out what each of these is, though, because we've got mass times gravity, and I've given you all the heights here. So it is a 50-gram ball, so we've got 0.05, 50 grams, times 10 for the G, times the height, which is 1.5. We know that that equals same mass, 0.05, times 10, because that's gravity, and then it only gets to 1, plus whatever the E thermal is. If you simplify those down, you get 0.75 equals 0.5 plus E thermal. And that lets you figure out that the thermal energy there then has to be 0.25. All right, so when we go through over here then, I'll just write it above on the bar graph. I'll say this is 0.75 on this side. Here we've got 0.5 for the energy there, and this is 0.25. It's not quite to scale, but because I was estimating originally, it doesn't matter about the scale. The last problem here, we've got a bow that's being used to launch here. It says an 18-gram arrow straight upward. The bow delivers an average force of 75 newtons to the arrow over a distance of 45 centimeters, and I want to know how high the arrow would fly before reaching its peak. So on this one, what we've got is a bow that you can consider the bow to be doing work on an arrow. I give you the force and the distance here, which is kind of a key that I might be going that route. And so what we've got then is we've got work on one side. All right, the work that the bow is going to do on the arrow is equal to the energy that the arrow receives, which is going to be used to get it to a high height. So we're going to say work equals final gravitational energy. The work that that bow does on the arrow is all going to be put into making it achieve this highest height. So force times distance equals mgh. All right, and then for our force, we've got 75 newtons times the distance, 45 centimeters is 0.45 meters, equals the mass, which I gave you as 18 grams. That's 0.018 kilograms. All right, times the gravitational constant, which is 10, times the height that it achieves. That's what we're trying to find there. And so if you go through and do that math, you should solve and find that the height equals 187.5 meters, which is actually a pretty impressive shot. Okay, so hopefully this practice using the work equation helps prepare you for what you might see on the exam. As always, if you have any questions about any of the problems on the sheet, make sure you come in and ask.